Docking is an important tool for modeling protein-ligand interactions. For example, the enzyme DHFR, dihydrofolate reductase, participates in the synthesis of tetrahydrofolate, which is an important cofactor in many biochemical processes, including nucleotide synthesis. Therefore, DHFR is an important target for various antibiotic and chemotherapeutic drugs. A few known drugs targeting DHFR are the antibiotic trimethoprim, antiparasitic pyrimethamine, and the chemotherapy drugs methotrexate and pemetrexed. For proper functioning, DHFR needs the cofactor NADPH as a reducing agent. This video will demonstrate the general functionality of the EnzyDocker module in CHARMM-GUI, which provides a convenient interface for enzyme-specific docking. The protein structure we'll use is 7MYM. 7MYM is a crystal structure of E. coli DHFR bound to the NADP cofactor and the antibiotic trimethoprim, denoted as TOP. We would like to dock trimethoprim into DHFR and check how well EnzyDocker can reproduce and rank the correct pose as one of the low-energy poses. To begin, go to EnzyDocker, type 7MYM, and click Next. We only select the segments we want to include, which are the first protein chain with its NADP cofactor named NAP and bound ligand named TOP. After selecting the three segments, click Next. If we want to modify the protein structure, this is where we would do it. To learn how to use the structure manipulation options, please see the video demos for PDB Reader and Manipulator. For most organic ligands and cofactors, we leave reading heterochain residues with default settings. For metal ions, one should specify the oxidation state through the Rename To and CSML Search options. In this case, we do not need to specify anything, so click Next to generate a CHARMM-compatible PDB file. When it finishes, you should inspect the structure to ensure that it was read correctly. Our structure is now ready to be submitted for the EnzyDocker demo, but we have to define a few additional settings before starting. First, we must define the binding site location, grid size, and grid resolution. The first docking stage is performed on a grid, and we should match the size of the grid to our ligand. Here, 20 angstrom should be enough, as it contains the entire ligand. It is okay if the cofactor is partially outside of the grid. The grid spacing affects the accuracy and the timing of the docking. Larger grids with finer spacing, for example 0.25 angstrom, will be larger than smaller grids with low resolution like 0.5 angstrom. We can visualize the size of the grid and its location. We offer 4 different ways for users to define a binding site for ligand docking. The first is to select the crystal ligand and center the grid on the ligand. The second is to select user-defined amino acid residues as the binding site, which is useful if the protein structure does not contain a bound ligand. The third way is to select a single amino acid residue and provide a radius around the residue. The fourth way is to predict a binding site using the VisGrid software, where users can select which predicted binding site is to be used for ligand docking. In our case, we choose the first option around the ligand TOP. Important residues can be flexible during docking to account for the effects of an induced fit. All residues within the grid are highlighted, and any of those can be chosen to be flexible. In this case, we choose ASP27, which is known to be important for ligand binding. Finally, we inspect the resulting grid and click Next. If we want to dock additional ligands, or if our protein structure doesn't contain any ligand, we can upload files describing the ligands in MOL2 or SDF format. Here we just click Next. On this page, we can edit the structure of the cofactors or the ligands with a 2D Marvin.js sketchpad. Here we want to adjust the protonation and oxidation state of our cofactor to verify that it appears in the NADPH reduced form rather than the oxidized NADP plus form. We check NAP to serve as our cofactor and remove it from the list of ligands to be docked, leaving Het B, which is the drug. We click Open to edit the cofactor. We adjust the charges and protonation states of the phosphate groups, the aromatic system, and the catalytic hydride. Before we click Next, we choose the option of matching elements to let the cofactor keep its experimental coordinates. To validate that the cofactor and ligand can be simulated using force field parameters from CGenFF, we click Check. If a red X appears, this means that CGenFF failed to generate parameters for this molecule, and the user should check whether there is a mistake in the structure or whether it contains unsupported atom types. Alternatively, the RTF, PRM, and MOL2 files can be uploaded in the previous step. Assuming we get a green check, we can continue. If we want to use the experimental ligand as a reference structure to guide our docking, we can define the reference ligand at the bottom of the screen. In this example, we will do free docking, so simply select NA, then click Next. Here we can inspect the protein, cofactor, and reference ligand structure and set a few docking options. We don't need restraints in this case. The other settings control the sampling conditions. If we have a large and flexible ligand, we may want to increase MC, which is the number of Monte Carlo steps, SA, which is the number of simulated annealing steps, and dock, which is the number of docking trials. If we get unreasonable conformations, we may want to decrease the upper SA temperature limit, but note that this also decreases the diversity of generated conformations. To score our poses using quantum methods, we can check the QMMM option, but this will increase docking time. We uncheck QMMM minimization to allow faster docking and before clicking Next. You can check the status of your job in the Job IDs page of your user profile. Once the docking is complete, we will inspect each pose's RMSD and energy. Here we see a list of docked poses. We see 31 poses with their scoring and RMSD. The sixth cluster contains 5 similar poses with relatively low energy among the top 3 and relatively low RMSD values. In contrast, the 11th pose has higher energy and RMSD values and is located partially outside the binding pocket. If we download the results, we can inspect them with PyMol or rerun the job using CHARMM on our own Linux or Mac machine with different settings. The directory contains all the information related to this job. The EnzyDocker results are located in the 7MYM directory, matching the PDB ID we chose, and all PDB files can be found in the results subdirectory. We can also transfer the entire 7MYM directory to a Linux machine with a compiled version of CHARMM and run it with different docking settings. Please check the EnzyDock GitHub for more information.